We make a number of different hydrates in the laboratory. Some are with hydrocarbons, methane being the most abundant. We also make carbon dioxide hydrate, ethane hydrate, propane, a number of different structures. So liquid nitrogen is very cold. It's about 100 degrees colder than the temperature at which these hydrate samples would dissociate, when they would decompose to ice plus gas on the tabletop. In here we have a little piece of methane hydrate. It's enclosed in a soft metal jacket. So the samples we make, they're polycrystalline. They look like snow, looks like compacted snow. But honestly, it does contain gas inside. Take a little piece off here, and as it warms up, you'll begin to see it pop. It's reverting to ice plus gas, and then as the ice would melt, as it continues to warm, it'll end up being water plus gas. So this will form anywhere you have water and gas at moderately low temperatures or high pressure.
My name is Steve Kirby. I'm a geophysicist here with the U.S. Geological Survey in Menlo Park. I work with Laura Stern, who's also a geophysicist in this lab that is devoted towards the investigation of planetary ices and gas hydrates.
Gas hydrates in nature occur in very remote places, and they are very complex with the sediment interactions and the conditions that they form under, and samples that are brought up are under some sort of alteration or decomposition.
We've educated ourselves by experiment in learning how to make them in a form that's suitable for doing material property testing.
We start in the main portion of the lab making ordinary water ice that we use as a reactant for the hydrates. And we grind and sieve that ice, and we pack them into pressure vessels. And we take that package and we put it into this freezer. And we load them onto these two ports. And we evacuate all the pore space between the ice grains. And then we have these reservoirs that have pre-chilled gas in them that we then put into that pore space to react with the ice to make hydrate. So we start simple, we make the pure end member hydrates, and then we add complexities in a known fashion so that the properties that we measure, we understand the individual effects of those complexities, unlike looking at just the samples retrieved from nature, which are so difficult to analyze. So this is a sample of, this is a structure 2 gas hydrate. It's predominantly methane, has a little bit of ethane in it. We're going to demonstrate how much gas is actually in this. If you bring a cubic meter of methane hydrate from the ocean floor up to the lab and put it on the tabletop, it would release 163 times its volume of gas at standard conditions. So it really is a very efficient way of storing gas. We're going to demonstrate that by lighting this sample on fire. So it's decomposing to ice plus gas. The gas is flaming, and the ice will soon just melt to water. And you can see it's not just a pile of snow that I was showing you.
They contain abundant amounts of natural gas. This natural gas is thought to be a significant potential resource for our energy needs later in this century.
This is a gas hydrate from the Cascadia margin. So this is a natural hydrate. It's brought up from the ocean floor. So you can see that the marine muds in here and these nice nodules of predominantly methane hydrate. So this laboratory is unique. Then we have the low temperature capabilities to make the samples. So we make different sorts of ice samples or gas hydrates or ammonia hydrates, both planetary ices and gas hydrates. And we also have unusual capabilities in how we look at those samples afterwards with the cryogenic capabilities on our X-ray diffractometer, as well as over in another laboratory, a cryogenic setup for the scanning electron microscopy, where we can actually look at the grain textures and pore structures of samples and how they interact with the sediments, how they look in nature compared to how we make them in the laboratory.
And lastly, we give insight from our laboratory experience as to the governing kind of physical processes that, say, govern their stability in nature, and how they respond to deformation, changes in pressure, and so on. So this is an unusual lab, but like I say, there are only a handful of them worldwide, and we are very fortunate to be here at the Geological Survey and to have the opportunity of working on them.